In this final screencast of Topic 5, we're going to analyze the performance of skipped lists. Okay, in order to analyze the complexity of the skipped list operations, the first thing we need to do here is to have some kind of bound on the expected height of the skipped list. How many levels are there in a skipped list? So I'm going to invent some notation here. Let's say x of 1 is the expected height of one item. In other words, if we insert one item, what's the probability that it occurs at any given level? So I'm going to write it like this: probability that one item inserted is in level 0 is 1. You always put it in the first level. The probability that one item is in level 1 is the probability of that one item being in level 0 times 1/2, because we flip a coin to ask whether it goes in that next level, right? But the probability of it being level 1 is 1, so that's simply 1/2. Okay, the probability that x of 1 is in level 2 is the probability that x1 is in level 1. But again, we flip a coin to see if we go up another level, is 1/2. But we've just determined that this is 1/2, so it's equal to 1/4. And you can now see the pattern. If we say that this is I, the probability that one item is in level I is going to be, of course, it's the probability. It's going to be the probability that it's in level I minus 1 times 1/2. But what it's going to end up being is 2 to the I, because that's the pattern here. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the I. So that's the probability of one item being in a level I. Now, if we want to ask, after we have entered n items, what's the probability that a given level has at least one item in it? In other words, the skip list is that high. I'm going to switch to the notation that the book uses here. So I'm going to say the probability that level I has at least one position is at most this probability here times n, because we get n chances to try to get it into each level. So it's bounded by that, because the probability that any one of n different events occurs is at most the sum of the probabilities that each event occurs. Now, we're interested in showing that these skip lists don't get more than a constant factor away from logarithmic. So what I'm going to do here is I'm going to set I, let's see, where shall I do this? Let's say I is some constant level of log n. And let's just plug that into this formula. So let's say the probability that the skip list is at most c log n is going to be less than or equal to n over 2 to the c log n. Well, what can we do with this 2 to the c log n bit here? Well, we're going to use the formula c log n is equal to log n to the c. That c is on the end there. So that lets us rewrite this formula. This is equal to n 2 log n to the c. But 2 to the log of something, base 2, is simply, this is the number that if you raise to the power, you get that number. So it's simply equal to n over n to the c, or in other words, 1 over n to the c minus 1. That is the probability that it's that high. So let's say if we want to bound it by 3, maybe. Let's say we don't want it to be any more than 3 higher than log n. So n to the 3 minus 1 is 2, n squared. So as n gets big, it's going to be bounded by 1 over n squared, which gets very, very small as n gets bigger. For example, if n is equal to 1,000, then the probability of it being higher than 3 log n is 1 in 1 million. A very long shot. So this is why we usually don't have to set an explicit bound on the height of the skip list. The chance of flipping a coin repeatedly heads and making the skip list really high is very, very low. So we're going to conclude that with very high probability, the height h is with very high probability order of log n. This is the conclusion we wanted. Now, using the result that the expected height of the skip list is order of log n, we need to ask the question, how long does it take to search one of these things? So we've got the height. The analogy is towards, height times width. How many levels do you have to examine, and how much work do you do at each level? So here we're going to figure out how much work you do at each level. That's going to be, we'll call that x of I is number of keys examined at level I. So how many keys are examined at level I? Well, when you scan forward in a list, if you examine a key, that key cannot also belong to level I plus 1. Why? Because if it did belong to level I plus 1, we would have found it in the previous scan, and we wouldn't be scanning forward to find it here. We would have just done the drop-down procedure that you can, the below that you see in the code. So the probability of finding any given key at some level is 1/2. Again, why? Because we flipped the coin to decide whether to put it up here, and that was with probability of 1/2. So the probability of counting the key at one level is 1/2. So when we're scanning forward, each time we scan forward, we're essentially doing something because some former coin toss gave tails that did not put it up there. So what's the expected number of times we must flip a coin before it comes up tails? Well, that's 2. So the expected number of scan forwards at each level is 2. So we now have our answer is 2. And we already had down here this lovely result that the height is order of log n. So we get the expected overall operation is a constant number of that. So the overall expected search time is log n for the entire data structure. It's pretty amazing that we only expect about a constant amount of scanning forward at each level, and then we get a logarithmic number of levels to scan. So this makes this data structure far superior to linked lists in performance, and based purely on random decisions about whether to build up the skip list to higher levels. So this data structure will be included in as one of the ones that you implement in your assignment, and you'll get to compare them to other ones like linked lists. Some things we have not talked about, well, the expected space requirement can be shown to be order of n. Essentially, you're going to get no more than 2n extra cells needed to store all of these extra things here beyond what you would have done just for the basic linked list. Left as an exercise for the student is rewriting the code so you can do the deletion and insertion on the way down rather than on the way up. That concludes our analysis of skip lists and of topic 5.